What's up, everybody? This is Matt Brown with another IoT hacking video. Today we have a IP camera that is not available in the United States market. I got this when I was traveling overseas to Southeast Asia, and we're going to take this apart over on the workbench. And today we are going to obtain root on this device over UART. So stay tuned for that. But if you're new to this channel, my name is Matt Brown. I am an IoT pen tester. That means it's my job to find security vulnerabilities in devices like these and report them back to manufacturers. And I like to educate people on this YouTube channel. So if that is something you're interested in, go ahead and hit that subscribe button. I would really appreciate it. And in this video, we are going to start a little mini series on the basics of IoT pen testing. What are the fundamental activities that someone like me, professionally, when they want to test one of these devices for security flaws, goes through? And so today we're going to do a hardware teardown, and we're going to look at physical debug interfaces on this device, and we're going to use those to obtain a root shell, like I mentioned. That's a spoiler alert. And then that is going to be a stepping stone for later steps of analysis on this device for security problems. Of course, some of those physical access issues might be considered things of great concern to the company in question, or they might not, but we are going to display them nonetheless in this video. So without further ado, let's head over to our workbench. And so here you can see this device. It is an Ochre. I have never heard of this brand before picking up this camera, and I doubt many have. It's a very cheap product. The English on here was clearly Google translated and not very well on this packaging. And like I said, I did pick this up over in Southeast Asia. I do not believe that this is available for purchase on the United States marketplace. And so if we set that aside, and we really only care about the actual camera, I've got some other stuff on the desk here that I want to talk about. Now, obviously, depending on the task, we're going to use some different tools here, but again, we're going over the basics in this video. So the basics, to start out with, we need to open up this device. So we're going to need some screwdrivers, some tools to open up our camera. And I've got a couple of options here that we're actually going to use kind of a little bit of both. I have my iFixit screwdriver set. This is an excellent set that has every weird kind of screwdriver bit that you could ever find on one of these devices. And then I also have these Wera screwdrivers, which are very nice. Let's just zoom in on those here. And these are really nice because sometimes you have a really long and narrow place to get a screw in, which is actually the case on this device. So this iFixit kit, although it is great, I cannot reach the screw down there. And so that's where these dedicated, so these are dedicated Phillips head screwdrivers, right? I can't switch out the bits. That's the con of these screwdrivers as opposed to the iFixit set. But these are very nice, well-made screwdrivers, and a lot of people like them. And so we're going to be using that as well for our kind of teardown of this device and when we look inside of it. And then the other thing I have on my desk is I've got a number of these probes, which if we zoom in on them, what we will see is that there is a needle on the end that is spring loaded. And so what this is going to allow us to do is it's going to allow us to probe things on our camera and connect to them without soldering. And that is really nice. Of course, I've got soldering equipment, but today we're not going to have to do any soldering in order to connect up to 3 places. We got 1, 2, 3 probes. One's going to be for ground, one for TX, one for RX on a standard UART connection, and we'll talk a little bit more about that later. But first, we want to talk about this right here. This is a TiGuard debug board, and so this board does many things, but the one thing that we're using it for today is its UART console here. So it has a ground, TX, and RX pins here, which are connected to the green, orange, and yellow wires respectively. And then the really nice thing that I like about this device is right over here. So we can see that it says, I don't want to mess this up, it says 5 volt, 3.3 volt, which is the setting it's set to right now, 1.8, and then target voltage, which it sets the voltage to whatever is powered over this pin right here. And so this allows us in one device to have a UART interface, a USB UART interface. So our USB cord is going to go right here, and then we can connect up to our device's UART console with these wires right here, in which, of course, those are connected to our probes. So those are the tools, and then obviously I've got a power cord and then a plug up here, which we will use to power on the device when we want to. So let's go ahead and plug that in. But I'm gonna up here, out of screen. You can see I have this to turn on and off. This is actually, this is kind of like, this is a little bit extra here, but this is like a hack that I use because sometimes I'll be probing things and I want to just like click a button really fast to turn the device on and off instead of like unplugging and plugging this thing back in, which can get annoying, and then you can bump things that are very delicate. Like if these probes are sitting somewhere that's very delicate and can get bumped off, it's easier to flip a switch. So that is our setup, and with that all out of the way, we are going to open up this device. So I'm going to set these tools off to the side. I think I'm going to use this one. So let's go ahead and zoom in here. And so you can see we've got 1, 2, 3, 4 screws we are going to have to remove. And okay, it's like, I think I unscrewed that and it's just like sitting down in the hole. So we just need to loosen those all the way. Oh, that one came out. Nice. Set that off to the side. Nice. And let's see. There we go. You don't need to be that zoomed in. Okay, that one also came out, but I think this will. All right, it's mostly coming off. I think this screw is our last holdout. There we go. And now we open that up and we can see the main circuit board on our device. And then this is a pan tilt zoom camera, meaning that the camera can, can move around in all directions. And so obviously up in here is going to be some motor components that are being driven by these wires. But what we really care about, now obviously if I were doing a full pen test, I would open this up and check that there's no important stuff up here. But for now, we're just going to assume, and my assumption is right in this case, that there's nothing really important up there. It's just motor driving circuits. And here is where all the important stuff is going to be. Obviously on this device, we have a power plug, a Ethernet port, and then on the back, we have a reset switch. And then we have some kind of like debug access here. I wonder if this was meant to be like a USB connection or something like that. And then on the side, we do have an SD card slot. So that's just kind of something that we would want to note if we were writing up a pen test report, all of the kind of access that there is to a system like that. Okay, so now you can see once we've opened it up, let's zoom in a little bit closer. We can see we've got one, two screws left on here that we are going to pull off. And so the goal that I always have in like when I'm doing the hardware analysis is, if it is possible, I want to extract the circuit board out of the device and get it to where it is functioning again outside of the case, because that's going to allow us to connect up to our target better. Let's just get that out of the way. All right, sweet, we got both of those. Got some tweezers too. I guess I didn't mention that in the tools. Always nice to have a couple sets of tweezers. All right, so now what we have is we have these, this little Wi-Fi antenna is connected here. These can always pop on and off pretty easily, just like that. And then if we want to connect this back up, right, like I said, my goal is to get it all hooked up outside of this case. And so I think I should just be able to like pull this through. Okay, and now we can ditch that. And now this can be nice and set up here on the desk. And I can make sure our Wi-Fi still is functional by popping this back on. And once you've done a couple of these, you kind of get used to it, but you just get it all lined up and then press in like that, and we're reconnected. So there we go. And now we can perform some enumeration. So like I said, this is not the most ideal situation because I still have all this stuff hooked up there, but we're gonna roll with that for today. So when we zoom in, we can already identify some potential critical components here. So, so right here and here, I'm spotting some things, and we're gonna go under the microscope so that you can see that better, because sometimes it's hard to see in this camera. So let's go to our microscope and give some light. And we'll go look at those components that I was talking about right here. So if I turn things the right way and focus us in, we can see that we have a clearly identified win bond 25Q128FVSG. So this is a flash chip. Just based on my experience, my eyes are drawn here, and then I literally recognize like these first, like, you know, like the 25, like a chip that starts with a 25. Those are very, very common 8-pin. You can see 4, 8-pin flash chips, and so very common. We are going to look at this in the next video when we talk about firmware extraction, because that is always the second step that I perform in any IoT pen test. The first one, funny enough, right here, right next door to the flash chip, is enumerating for debug interfaces. And on this board, let's turn it around so we can read this. They have nicely labeled the debug interface for us, so we don't have to do any kind of reversing of the pinout of this thing here. We can clearly see we have a 3-volt, an RX, a TX, and a ground. And this is just so obviously the UART console of our device. Now, if these weren't marked, the process that I would follow is I would probe all of these and check what is connected to ground. Well, where can you always find a connection to ground? Well, a lot of times things that are like metal, like this, you know, the shield of here or this shield on the SD card, those are always metal. Another thing to know is that Wi-Fi antennas are always grounded. So if I probed there and I saw if there was a connection to this pin, I would know that this is ground. Knowing ground is not important because you can always connect to that anywhere on the system, but it eliminates, if you see a set of 4 through-hole pins that are unpopulated like this, that's always the sign of the UART on the PCB. And by finding the ground, you eliminate 1 out of 4 that are not the things you're looking for, and that's RX and TX. The first thing you're going to look for is TX, because then I'm going to probe around when I start the device, and I'm going to see voltage fluctuations. So after you find voltage fluctuations, you can connect up to it with our probes, which is what we're going to do right now because it's all marked out for us. Like I said, we would normally use a multimeter to kind of examine things, but they've kind of helped us out here. So what I'm going to do actually is I'm going to raise this up. So this just happens to come. Oh, let me throw that back into focus mode for you guys. These are these nice little stands that also come with these PCBite probes. So all helpful stuff. So what we want to do though is let's zoom in all the way on our UART interface here, and we're going to connect up to it. So we're going to connect up to ground, like so, and then to the one that is marked TX, we are going to actually connect our RX of our UART board, our tie guard board here. And that is because you want them, like, your computer should be transmitting to the receive of the system and, vice versa. So there we go. I believe those connections are solid, and we will be able to test that in a minute. And I realize I should have plugged this system in before I set all those probes carefully on there, but okay, we got that set up. So now we're plugged in, and then I also have to plug in my tie guard board here over USB, and now we should be ready to go. So what we're going to do on our computer, so the tie guard, it shows up on my Linux system here. You can see tie guard v1.1. securinghardware.com. Go there to find the sort. Like if you want to buy one of those tie guard boards, you can go there. I think it's on. It's not Kickstarter, but it's another one of those like Kickstarter like websites that sells it. So definitely go check that out. And you can see it creates these two FTDI USB serial devices on TTY USB 0, and one TTY USB 0 is the one that we want. If you already had a device hooked up that took the place of TTY USB 1, it would be like there'd be two of them, and it's always going to be the first one. So what we're going to do is we are going to use PicoCom. You can use Minicom, PicoCom, any kind of terminal emulator. We're going to pass it the default baud rate of 115/200. That is like always just like the standard baud rate that exists on these devices. Sometimes you have to fiddle with that, but most of the time it's going to be this baud rate. That's just the data rate. That's like how many symbols are sent per second. And then we're going to, of course, pass it the path to dev TTY USB 0. And we're going to hit enter. And then if I have all these pins set up correctly, I can go ahead and power this on and cross my fingers. And then, aha, it is working. Okay, cool. So we can see a bunch of stuff scrolling by, right? If you've ever booted a Linux system and like had a monitor hooked up to the computer, or saw like the kernel logs booting up, it would look something like this, right? And that's what we're getting. We're getting some output from userland, like userland programs, and from the Linux kernel and the whole boot process of the device. Now, this system tells us something really interesting right here. It says, press Q, enter to exit boot procedure. Like, okay, that's interesting. That's a good thing to note. Anytime it tells you to press a key, generally in an IoT pen test, we should try to press the key that it's telling us to press, right? Those are always interesting. But let's actually scroll up here. And we see like a bunch of useful stuff. And in a pen test, what I'm going to do is I'm always going to capture like the entire boot up process where I don't interfere with it at all, and throw that away in a log file and that I can refer back to. And there's all sorts of useful information about the system that gets displayed on boot up. Let's see if we can find some. Here is one of the helpful pieces of information I always like to find, and is very helpful in future stages. So again, we're doing the basics in this video series. Today we're just looking at this hardware debug interface, this UART interface, but next video we're going to do firmware extraction. We're going to take that flash chip off, and it would be nice to have the partition table. Well, here it is in this UART log. It's telling us, okay, there's 5 partitions on this flash chip, and the offsets and, from start to end of each partition. So this is great. So then when we dump later the file, we can very easily carve out all 5 partitions into separate files. So very helpful information. We can scroll up some more and we will see okay, so like our Linux version 3.3, and we should see the kernel command line. The kernel command line is, again, it's like the arguments that are passed to the kernel when it's booted up, and those are always very interesting. If you can change those, sometimes you can gain access to the system that you wouldn't otherwise have. That's super interesting. We also see it say, hit any key to stop auto boot 0. So potentially we can get into the bootloader of this device. We'll try that in a minute. And then we have the top. So if I hit enter down here, I don't get anything. But remember, it told me to like hit Q and then hit enter. So let's just try that. And it says it's like exiting things and it's actually stopping a bunch of programs. And then it just drops us into a root shell, which is super nice, right? It's very nice of them to do that for us. Thank you. Thank you, guys. So from here, one of the cool things is now that we have root access, so sometimes on on a system like this, you'll get root access, but then it will not have all the file systems mounted. But here, we actually do have the root file system mounted, which is useful, right? I don't know. Oh yeah, so right here is probably where our like dynamic data sits. So this is like a little bit of like a 102 hints of how these systems are built. A lot of times on IoT devices, I would say mostly for stability reasons, so that the device doesn't actually accidentally get into a bricked state. Many of the critical components on that system are stored in a read-only file system. Now you might say, okay, this rootfs, it says that it's read-write, but here we see that /dev/root is mounted on / and it's type squashfs. Now squashfs, by its very nature, in its implementation inside of the kernel, it is read-only, right? You cannot mount a squashfs file system as read-write and make it writable, right? Like if you want to change something inside of squashfs, you have to regenerate the file system and flash it fresh to the chip or write it to memory, to storage, right? So, but we have another file system here that is JFFS2, and we see that this is MTD block 3, and okay, so there's a thing that you can always cat out. I think it's this, where we can get that same exact information that we saw, more or less. It's a little bit different format, but that same partition table. So this is great. And so here we see MTD block 3, which is just a block device that is related to MTD3. And it says that this partition is named user 0, and user 0 is mounted on mount MTD, which is very interesting. So here, there is a bunch of stuff that is like writable, right? This is where anything is put if you want to write to the system. So that's really useful, and we can investigate this. Let's look inside onVIF. So onVIF, if you're not familiar, is a standard set of APIs for video devices. So that's pretty interesting. Okay, it says there's some kind of like a user list. Let's not there. All right, they're like a config. That's just some binary file. But you can see that this root shell is extremely useful for letting us go through things. Oh, I'll show you one more thing. There is a password hash that to date I have not been able to crack this, but I will post this in the description of this video, and if somebody out there wants to try to crack this hash, more power to you, and then comment back in the video if you've cracked it, and I will show that off in the next video if you get that done. That would be sweet. So There's some other cool files here. Obviously, like we could go through these for a while. rtsp.ini. Okay, so that's like some different RTSP. RTSP is a video streaming protocol, and so that's cool. Okay, so these paths are useful sometimes because those are like oftentimes like part of the URL that you would make a request to in order to like request videos for like a video stream from the device. That's useful pieces of information. Sometimes if there wasn't authentication properly set up for RTSP, if you knew these paths, then you could connect and get a video stream from the device. Yeah, all really interesting stuff. Let's look at like one more file because this is just kind of fun. Ooh, there's a comp folder, actually. Let's go inside there. Okay, a bunch of interesting stuff there. Is there like any kind of like, let's grep for like like password, right? How big are these files? Then I go through it very. I think this device is just very slow. All right, let me just like cat out one of these. Oh, okay, they're like binary files. Interesting. All right, let's look at scope. That's cool. Okay, so again, more information about potentially some of the OnVIF services that are related on the device. But you can see in this video that we unpacked. We took apart the camera, and just with finding this UART access, we have a host of information that we have access to now. Now, I want to look at the bootloader too, because there was that potential to get into the bootloader, and I'm going to turn it off, and then I'm going to get ready to hit enter really fast when we turn the device back on, and you can see that we were able to get into the bootloader, right? So that hit any key to stop auto boot. So that's why, you know, when you turn the device off, turn it on, and you hit enter really fast. And so this is another thing we can do with debug access to the system is we can get access to the bootloader. And sometimes, if you don't have just like a key to give you a root shell, like this device has, sometimes you can use this U-boot menu here to give yourself a root shell anyway. I have not tried this on this device yet. I've never been in here. So this is fresh. We're doing this live, all right? So, this is just fun stuff. So, okay, the first thing I always look for in these U-boot, did it call itself U-boot? Yeah, here, it's obviously U-boot. I can just tell from all the names of these commands, but print env is always my first thing that I want to run because it's going to give us a bunch of environmental variables. And this is really interesting. Okay, so we have command. These are obviously the command line kernel arguments here. And so that's so interesting. Okay, so here's this boot command here. All right. I'm trying to see like if we were to like try to modify one of these, which one would we want to modify? Huh. That's interesting. Because sometimes you can use this to just directly drop yourself into a boot shell. And the way that we would do that is, I don't know which one of these is actually being executed. Okay, it's some difference in the amount of memory. Which command is being used? Somewhere here, it's going to be like run command 1 or 2 or 3 or 4. Huh. Well, that's funny. All right, we're just gonna YOLO this thing, and we'll see what happens. So command 1 will do. Okay, so help, and we can see that there's the save. Set env. We want to do set env. Command 1, and then we do space, and we do all this stuff. Oh, okay. So it says init. Okay, so we have to change this. All right, so we have to change, you know what, let's just come down here and let's make a little text file. That's our change. Okay, so we're gonna do set env, command 1. Oh, we can change all of them this way, actually. There we go. We can be thorough. There they all are. And then we can say, go to squash. Okay, so instead of squash fs, we want to boot directly into bin sh. Bin sh. I obviously could have done a find and replace and done that way faster, but here we are, guys. And bin sh. Okay, so what I want to do is I want to turn these all into commands that we go like this. Set, okay, we can do it like this. Set env space. There we go. We got our commands. I don't know if I'm supposed to put it like all in quotes. So that's the one thing I don't know about, guys. Print env. Let's look at all our things. Did we fix it? Hey, they're updated. I like it. All right. Wait. What happened there? Was that always there? You know what? YOLO. We're going to run boot. We're going to find out if this drops us into our emergency shell here. Kernel panic. It didn't like it. It was not happy with us, guys. All right. Well, but you get the idea. So, but it did. It did update. It did try to execute bin sh. But maybe this system has a different shell. That's so interesting. All right. You guys get the point of the video by here, but now this is just like, this is fun. We're doing this live. I've not succeeded in getting the root shell via this method yet, but we're gonna try to get it. Okay, so and then a good thing to know about set env, unless you run the save env command, it doesn't persist it to storage any of these config changes. So now I just powered off the device, and so now you'll see all of these are set back to what they were. Oh, wait, no. I just want to boot normally. Yeah, I have to boot normally, and I have to see like what shell actually exists on the system. Okay, so, and I can do my like Q enter thing. I think it could do it early. Maybe it can't do it early. Maybe I gotta let it, okay, Q. Come on. Let's go. Hey, there we go. What? So bin sh does exist? What gives? Okay, init bin sh. It doesn't like it. What about busybox? Like, can you busybox? Well, but then no, you can't do that. All right. Is there like dash bash? All right. But you guys get the point. We're obviously able to do a bunch of stuff with the system through that bootloader shell, and sometimes you can use it to pop yourself into a root shell from bootloader access, right? So if we were writing this up in a pen test report, like what would we kind of like write up as like a finding here? So one, the bootloader is unlocked. Actually, I should go back a step. What I don't write up is, what I'm not gonna write them up for is like, you labeled the PCB. You should pour glue and epoxy and make it really hard for them to have UART access. Like, sure, if you're like really trying to harden the device down, you could do that, but that's not really a vulnerability, right? That would just be security through obscurity, which is not how we do things. We shouldn't do it that way. But what I would write them up for is the bootloader being open, right? It's not locked down, it's not password protected. That is something that people care about in their threat model. Some people don't care about it, but we're still gonna write them up for it. And then the other thing is obviously having that like debug access to just hit Q and enter and just drop yourself into a root shell without any kind of a login, right? Again, like I mentioned, like to date, I cannot crack that password hash. That is a hard-coded password, which is probably not a good thing. It's kind of like backdoor potential, right? But we would still, but still, like if you have a regular login on that shell, I would not be able to get into it yet. So that. Those are the two major things we would write them up for. Thank you for watching this video, and next we're going to use some of the data we've gathered here over the shell, and we're going to physically remove the flash chip on our device and show you the next step of the IoT pen testing process, which is firmware extraction and analysis. So thank you and have a great day.